Hello everyone. Last time we covered part of the respiratory one, so now let's continue our lecture. What is intrapleural pressure? Let's take a look at this diagram. Let's say this is your lung, this one, and your lung is being covered by visceral pleura, which is this line, and then you have a parietal pleura, which is this one, which is attached to the chest wall, which is this brown one. The space between visceral pleura and parietal pleura, this space is called intrapleural space. And we mentioned the pressure inside the intrapleural is negative. In other words, the pressure outside is 0, the pressure inside the alveolus is 0, and the pressure here is -5. I hope you remember we said in reality the pressure outside is 760 millimeters of mercury. If I open my mouth, then the pressure outside the body here and the pressure inside the lung becomes equal, 760 millimeters of mercury, and pressure inside the pleura, this space, is 5 points less, so it's going to be 755. Instead of saying 760 and 755, we said we're going to show this one as a 0, then we show this one as -5. So now, if I open my mouth and I don't breathe, the pressure outside is considered 0, the pressure inside my lung is considered 0, and the pressure inside my pleural space is -5. Remember we said the negative pressure, like a vacuum, is going to pull everything toward itself. So therefore, the difference between this 0 and this -5 would be 5 points of the force that pull this visceral pleura toward outside. As a result, my lung stays open. Now, if you try to breathe in, your diaphragm is going to go down, the diaphragm attached to this parietal layer. Your chest is going to move to the side. That means you're going to pull parietal, because parietal is attached to the chest. You're going to pull it toward the outside also. As a result, the negative pressure inside the lung increases from -5 to, let's say, -6.5. Therefore, the amount of force that's going to pull this visceral parietal also is going to increase. As you increase this intrapleural pressure from -5, let's say, to -8, as you can see, my vacuum also is going to get stronger and it's going to open up my lung even more. Now the pressure inside the alveolus is going to go below 0 and air is going to come in. Air is going to come in until the pressure outside and inside becomes equal again. When you try to breathe out, the chest is going to go back again. The diaphragm is going to move up. Therefore, the pressure inside this intrapleural space becomes less negative. And when it becomes less negative, there is less vacuum, and this force is going to get smaller and smaller, so this visceral pleura is going to move toward inside, the pressure here is going to go up. When the pressure here is bigger than pressure outside, air is going to get out. So let's do it one more time. When you are not breathing, the pressure outside is 0, the pressure inside the alveolus is 0. The pressure inside the intrapleural space is negative -5. As a result, there's 5 millimeters of mercury force that pulls this visceral parietal layer toward out. That's why it shows +5. Remember, parietal is attached to the chest wall and also attached to the diaphragm. When the diaphragm goes down and your chest is going to expand, that means this parietal one is going to move out and this parietal one is going to come down. That means this space is going to get bigger. When the space gets bigger, the pressure is going to drop further. So let's say it's going to go from -5 to -6 to -8. When the pressure goes down, becomes more negative, it's going to pull this visceral layer more toward the outside. As you can see, forcing that pull this visceral out is going to increase from +5 to +5.5 to +8. As you pull this visceral out, the space inside the lung also is going to expand. When the space increases, as a result, the pressure inside the lung is going to go down and air is going to go from higher pressure to lower pressure. So air is going to come in. Air is going to come in until the pressure here and here becomes equal. This is the end of inspiration. Now, when you do an expiration, diaphragm is going to move up. The chest is going to move in. That means space is going to get smaller. When the space gets smaller, the pressure is going to go up. That means -8 is going to change to -7. It's going to change to -6. It's going to change to -5. It's going to go back toward normal. And as this pressure is going to become less negative, that means there is less force to suck this visceral layer out. As a result, the visceral layer also is going to get closer to each other. Pressure inside the lung goes up, and as a result, the pressure here is going to be more than pressure outside. Air is going to go out. Air is going to keep going out until the pressure here and here becomes equal, and expiration is going to stop, and the cycle is going to continue. As you can see in this picture, this negative pressure here is really important. Why? Because if, let's say, someone is going to get shot or stabbed, or somehow you're going to poke the wall of your chest, what is going to happen? Well, the answer is air is going to get sucked in, because here's a vacuum, so air is going to go from higher pressure to lower pressure. As you lose the negative pressure here, there is nothing to pull this lung out. Remember, you pull your lung out because of negative pressure inside the intrapleural space. So if you lose the negative pressure here, your lung is going to collapse. So as a result, it's called pneumothorax, when the air gets inside the intrapleural space and your lung is going to collapse. Now, let's go one step further and make sure we understand one more thing, and that is this. This negative pressure here in the normal situation, yes, is going to pull this visceral layer out, but also is going to pull this parietal layer in. It's a negative pressure, is going to suck things toward itself. So it's going to suck this one this way, and it's going to suck this one this way. This chest wall is like a spring. If you have a spring and you push it down and hold it, as soon as you let it go, the spring is going to open up, it's going to snap out. This negative pressure not only is going to pull the visceral layer out, but also is going to bring this parietal layer more in. As soon as you puncture the chest wall, like this one, and the air comes in, and you lose this negative pressure, your visceral layer is going to collapse. So lung is going to collapse. But also your chest wall is going to spring out. That's why you see this dashes is going to move out. After learning this one, let's talk about compliance. What is compliance? Compliance simply means how easily you can expand your lung. If I expand my lung easily, I say my lung has a higher compliance. If it's hard for me to expand my lung, I say the lung has lower compliance. I want you to think about this example. Let's say I have two rubbers. One is a thin rubber and one is thick rubber. When I pull the thin rubber, I can pull it easily. When I let it go, it's going to collapse. However, in the case of thick rubber, if I try to pull it, I'm going to feel more resistance. But when I let it go, it's going to recoil, it's going to bounce back much faster. In other words, the thicker rubber has lower compliance because I have to pull it harder to be able to expand it, and the thinner rubber has a better compliance. If I can expand a lung easily, that means my lung has a higher compliance. If I have to put so much pressure to open my lung has lower compliance. You need to understand that compliance depends on the elastic property of the lung. It's called elastance. When the elastance or elastic property of the lung is higher, the lung is going to have lower compliance. The formula for compliance would be delta V divided by delta P. How much you can change the volume by changing the pressure. To understand this one, let's take a look at an example. Let's say the intrapleural space in the lung in a normal person is minus 4 millimeter of mercury. In the previous example, we said -5, but it doesn't matter. Let's say when you breathe in, your chest is going to move out and your diaphragm is going to come down, and the pressure inside the intrapleural space is going to decrease to -7. As a result, air is going to come in, as we explained. And let's say because of that, you bring in 600 ml of air, and that's called tidal volume. So you change your intrapleural space from -4 to -7. As a result, you brought 600 ml air. What is the compliance of this lung? Well, the answer is I brought 600 ml for the difference of 3 millimeters of mercury. That means my lung compliance would be 600 divided by 3, which is 200 millimeters of mercury. That means for every drop of intrapleural space, I could bring in 200 ml. From -4 to -5, 200. From -5 to -6, 200. And from -6 to -7, 200. This is the compliance of this lung. In another example, I'm going to change the intrapleural space from -4 to -7. But I bring, let's say, in 900 ml. That means my compliance would be 300. In this example, by changing the same pressure, you bring more air in. That means your lung is going to expand much easier. So in this example, the compliance is 300. In previous example, the compliance was 200. That means this lung has a better compliance. A better compliance, that means less elastance, less elastic fiber. So now let's take a look at this example. Here is two alveoli. We have millions and millions of alveoli in our lungs. Not all of them, they have the same size. Let's say in this case, this alveolus is half of the size of this one. This one is twice as big as this one. The radius for this one is 1 and radius for this one is 2. To keep an alveolus open, there are two forces that we have to overcome. One is elasticity, that we have to, like a rubber, we have to pull the rubber. And the second one is surface tension. However, because of surfactant, the surface tension becomes 0. Therefore, the only thing that we have to deal with is the elasticity for the wall of the lung, or compliance of the wall of the alveolus, because surface tension is not a problem because of surfactant. Now, let's explore the idea of surface tension here in a little bit more detail. Remember we said inside the lung we have a small amount of water, and that is going to try to collapse the lung. So if I want to open this alveolus, I have to create enough force that overcome the elasticity of the wall of the alveolus, and also I have to overcome the surface tension. Laplace came and said, okay, how much force I have to apply to this alveolus to overcome the surface tension? Here in this formula, surface tension is shown by T. Clearly, the smaller the radius, the bigger the surface tension. In other words, when you have a smaller alveolus, you have to apply more force. Let me make sure you understand. Let's say in this example, I want to know how much force I have to apply to overcome the surface tension. Based on this formula, let's punch in the number. In this formula, for R, I'm going to put 1. So to keep this one open, the amount of force that I have to apply is twice as surface tension. Whatever the surface tension is, I have to apply twice of surface tension. If I put R here as 2, the amount of force that I have to apply to keep this one open is equal to surface tension. In other words, to keep the smaller alveolus open, I have to apply twice as much of force compared to this one. This one is going to open up if I apply the force equal to surface tension. Here I have to apply twice force to open this alveolus. A smaller alveolus needs more force to stay open. So that is going to cause trouble. If that's the case, when the air comes here, air is going to say, should I go this way or this way? Obviously, air is going to choose where it has to apply less force. So that means air is going to come here. Do you see what's going to happen? When you breathe in, then all of a sudden, all of your smaller alveoli are going to collapse and the air is going to go to the bigger alveoli. All of a sudden, all of your alveoli are going to collapse and you're going to have one lung with one alveolus. That makes no sense. To prevent this problem, we said we're going to use surfactant. So now you understand why surfactant is important, because surfactant is going to break up this surface tension. As a result, the force that you apply to open this alveolus would be equal to 0, because if the surface tension becomes 0, then the amount of force you apply to overcome the surface tension is 0. That's why in a normal lung, the only thing that is going to determine the compliance is elasticity of the lung, not the surface tension. You have to understand, to keep an alveolus open, there are two forces that we have to overcome. One is elasticity, that we have to, and the second one is surface tension. However, because of surfactant, the surface tension becomes 0. Therefore, the only thing that we have to deal with is the elasticity for the wall of the lung, because surface tension is not a problem because of surfactant.